Hello and welcome. In this session, I want us to do an example of evaluating an integral using the Gauss Legendre 1-point and 2-point methods. The 1 point is given by the integral from -1 to 1 f of x dx is equals to 2 times f of 0, while the 2-point method is given by this other expression here. So I want to evaluate an integral, and we take an example. The example we are going to have is the integral 0 to 1. Then we have e raised to power x divided by 1 plus x dx. So that our function we have here, but the problem is that the limits of integration are 0 to 1, while as per the methods, the method is the lower limit is -1. So we are going to start by transforming the limits of integration to have 1 and -1. So any interval AB can, the closed interval in this case, can always be transformed to -1, 1, using the transformation x is equals to b minus a divided by 2 times t plus b plus a divided by 2. So we are going to use this transformation to transform our interval. So in this case, we have x is equals to 1 minus 0 divided by 2 times t plus 1 plus 0 all over 2, which is a half into t plus 1. We say that dx by dt is equals to a half, meaning that in this case dx is equals to a half dt. So our integral, which is the integral 0 to 1 e raised to power x divided by 1 plus x dx, can now be expressed as integral from -1 to 1. We have e raised to power a half into t plus 1 divided by 1 plus a half into t plus 1, then times a half dt. If we simplify this, we can get -1 to 1 e raised to power a half into t plus 1 divided by t plus 3 dt. So that our function f of t now is this one. So we see that we have the function f of t, which is e raised to power 1 over 2 into t plus 1 divided by t plus 3. So using the 1-point method, the 1-point method says that the integral from -1 to 1 f of t dt is equals to 2 times f of 0. So that in our case, we'll have 2 multiplied by e raised to power 1 all over 2, 0 plus 1, divided by 0 plus 3. So when we work out this, we get the value is 1.0991. If we use the 2-point method, the integral from -1 to 1 f of t dt is equals to f of -1 over the square root of 3 plus f of 1 all over the square root of 3. So remember our function. Our function is e raised to power half into t plus 1 divided by t plus 3. So we evaluate that at the point -1 over root 3 and +1 over root 3, then add. So we have, this will be e raised to power half into -1 all over root 3 plus 1 divided by -1 over root 3 plus 3, then plus e raised to power 1 all over 2, 1 all over root 3 plus 1 divided by 1 all over the square root of 3 plus 3. We work out this, and when we work out this, you can take your calculator and work out. You get 1.1250. This is the approximation to that integral when using the 2-point method. So basically those are the 1-point and 2-point method. Suppose we are given another probably a different problem. You are given a method. You are given a method, say the integral from 0 to 2 f of x dx is equals to a times f of 0 plus b times f of 0.8 plus c times f of 1.8. And then you're told to determine the values of a, b, and c. Here, a, b, and c are constants. So you want to determine the values of a, b, and c such that this method is made exact for a polynomial of the highest degree possible. So if we want to do that, to solve that problem, we first note that the method, the integration method here, has 3 unknowns. The unknowns are a, b, and c. So it has 3 unknowns, and so the method can be made exact for a polynomial of up to degree 2. So in this case, we could substitute f of x is equals to either 1 is equals to x or x squared. So the method can be made exact for a polynomial of up to degree 2. 1 is a constant polynomial or a constant function. X is an identity function. Then we have x squared. So when if we take the case when f of x is equals to 1, then it means that f of 0 will be equals to 1. F of 1.8 is also equals to 1, and f of 0.8 is also 1, because this one is a constant function with a value 1 everywhere. So our method can be expressed as integral from 0 to 2, 1 dx is equals to a times 1 plus b times 1 plus c times 1. So that when we integrate here, we get x from 0 to 2 is equals to a plus b plus c, or even we get a plus b plus c is equals to 2. That's an equation with 3 unknowns. So if we consider a second case now, when f of x is equals to x, then we see that f of 0 will be equals to 0. F of 0.8 will be equals to 0.8, and f of 1.8 will be equals to 1.8, because this is an identity function. So in this case, when we substitute, we get the integral from 0 to 2 f of x dx, which we would write a f of 0 plus b f of 0.8 plus c f of 1.8. We get, we are substituting f of x is equals to x. So on the left hand side, we have 0 to 2 x dx is equals to a times 0 plus b times 0.8 plus c times 1.8. If we work out this integral, we get a half x squared from 0 to 2 is equals to 0.8b plus 1.8c. So that this will be a half multiplying 4 minus 0, which is 2. So we get the equation 0.8b plus 1.8c is equals to 2. So we have that second equation. And if we consider the last case, when f of x is equals to x squared, then we see that f of 0 will be 0 squared, which is 0. F of 0.8 will be 0.8 squared, which is 0.64. And f of 1.8 will be 1.8 squared, which is 3.24. If we substitute, we get the integral from 0 to 2. F of x is x squared, which is a times 0 plus b times 0.64 plus c times 3.24. And integration here will give us 1 over 3 x cubed from 0 to 2 is equals to 0.64b plus 3.24c, so that we get the equation 0.64b plus 3.24c is equals to 8 divided by 3. This is the third equation. Now we have three equations. The first one is a plus b plus c is equals to 2. The second one we have 0.8b plus 1.8c is equals to 2. And the third equation is the one we have here, which is 0.64 plus 3.24c is equals to 8 over 3. So now the problem now is to solve these equations to find the values of a, b, and c. If you take the last two equations, the last two equations do not have a, so we can get b using maybe the Cramer's rule. The denominator can be expressed as 0.8, 0.64, 1.8, 3.24. The determinant of that, the numerator would be 2, 8 over 3, and then we have 1.8, 3.24. If you work out this determinant and divide, you'll get the value of b as 7 divided by 6. Now, once we get the value of b, we can pick one of the equation, like this one, for example, and make c the subject, so that we get c would be 1 divided by 1.8, then 2 minus, see that we just need to move 0.8b to this side, so that we have 2 minus 0.8b divided by 1.8. 0.8b. Remember, the value of b is 7 over 6. So when we substitute, we can get the value of c as 16 all over 27. Then from the first equation, we had a plus b plus c is equals to 2, meaning that a can be expressed as 2 minus b plus c. Because we have the values of b and c, b is 7 over 6 and c is 16 over 27, then we just substitute and get a is 13 all over 13 over, so this is 13 over 54. So that we have our integration method. Our integration method, remember, we have now a is 13 over 54, b is 7 over 6, and c is 16 over 27. And remember how our integration method looks like. I want to go back to where we started. So we just need to substitute the values of a, b, and c. The values of a, b, and c there. I don't have enough space there down there. So I want to come back here, and maybe I'll remove this part, then substitute, so that our method will become 13 alpha 54 f of 0 plus 7 alpha 6 f of 0.8, then plus C is 16 over 27 f of 1.8. So now you may be taught maybe to evaluate an integral using this method. Maybe you are given an integral from 0 to 2, and say you have e raised to power 2x divided by 1 plus x squared. All you need to see is that our function is e raised to power 2x divided by 1 plus x squared. So we simply write this. One as 13 alpha 54, and then f of 0 will be e raised to power 0 divided by 1 plus 0, then plus 7 alpha 6. F of 0.8 will be e raised to power 0.8 times 2, which is 1.6, divided by 1 plus 0.8 squared, which is 0.64. Then plus 16 alpha 27. F of 1.8 will be e raised to power 1.8 times 2 is 3.6, divided by 1 plus 1.8 squared, which is 3.24. And this is all we need to work out. And if we work out this, we can get a value of 8.89, 8.8793 approximately, correct to 4 decimal places. So application of the method. Once the method is determined, it is just a matter of evaluating the value of the function at each of these points and then substituting. Then we get the solution. So basically that is how we can use this, we can solve such a problem. First, we note that the method has 3 unknowns, so it can be made exact for a polynomial of up to degree 2, which is 1 less than the number of the unknown, so that we write f of x, the takes either 1x or x squared, in this case, up to degree 2. Then we start now substituting. F of x is 1, f of x is equals to x, f of x is equals to x squared. So that will give us 3 equations in 3 unknowns. Then we solve the 3 equations to get the values of a, b, and c. And lastly, we come back and substitute. If then we are given a problem to solve using the method, then it's a matter of evaluating the value of the function at those points. So basically that is the method. We call this method, such methods, as the methods of undetermined coefficients, because we have some coefficients which we need to determine. So thank you for watching.